In our previous video, we conducted an entire simulation study to investigate to investigate the relationship between the marriage views and generation. So we wanted to know whether there was an association between whether people felt that marriage was obsolete and their generation being whether they were millennial, boomer, Gen Xer, or whether they were over the age of 65. We did a simulation study in which we broke the association or broke the link between marriage views and the generation, and we generated a whole bunch, about 1,000 chi-squared statistics. And we looked at the distribution of the statistic, and we found that our statistic was very, very large relative to the bulk of the statistics that we would have expected if there were no association. What we're going to do today is look at what the theoretical chi-squared distribution looks like. So this should be a fairly short video. And I'm going to interject here that I'm always very happy to find when I've pre-recorded videos from previous semesters that I don't have to make as many videos as I previously anticipated. So what is the chi-squared distribution? The first thing I'm going to say is that it is the chi-squared with a D distribution and not the chi-square distribution. The chi-squared distribution is based on the Greek letter chi, and it is based on squared values. We saw in our previous video that we were actually going to take our observed counts and our expected counts. We took the difference for each cell and squared them, and that is why it is chi squared. When we go to jump, I'm going to show you what the chi-squared distribution looks like, and I'll also show you how jump calls it the chi-square distribution, and in this case jump is wrong, just in the name of the distribution. When we do something like 2 squared, we don't call it 2 square, we call it 2 squared. And so when we have the chi-squared distribution, we don't call it chi-square, we call it chi-squared. And so now when you go out into the real world and you hear people talking about the chi-squared test of independence and the chi-squared test of goodness of fit, you know that it should have a D on the end, and you can correct them, and you can say that you were taught correctly by Dr. Megan Lutz at the University of Georgia. So that is my little aside. So what is the chi-squared distribution? Well, the first thing we want to know is that because it is based on squared values, it will always have positive values. So just like the F, which is based on variances, so it is based on squared things, the chi-squared, being based on squared things as well, will always be positive. So it is impossible to have a negative chi-squared value. You can't have negative squared values, so you can't have a negative chi-squared. Like the T distribution, it is based on a degrees of freedom parameter. So depending on the degrees of freedom, that's going to change the shape of the chi-squared distribution. In this case, the degrees of freedom for the chi-squared test of independence is going to be the number of rows minus 1 times the number of columns minus 1. Or we might abbreviate this as R minus 1 times C minus 1, where R is the number of rows and C is the number of columns. We know that this can be found because if we know that the rows have to sum up to a total, then whatever that last row is going to be dependent on the sum of the previous R minus 1 rows. And if all the columns have to sum up to something, if there is a column sum, then we know that whatever that last column is has to be a function, is dependent on whatever all those previous columns are. So we have R minus 1 times C minus 1 degrees of freedom. So once we know the degrees of freedom, so the degrees of freedom is the parameter for the chi-squared distribution, that tells us what the mean of the degrees of freedom the mean of the chi-squared distribution is. So the mean of the chi-squared distribution is the degrees of freedom. So as we get more and more degrees of freedom, so that is as the number of rows and or the number of columns of our contingency table increases, the mean of the distribution that this statistic comes from also increases. We also know that the standard deviation of the chi-squared distribution is the square root of 2 times the degrees of freedom. So as the degrees of freedom increases, the standard deviation also increases. So with more and more degrees of freedom, the more and more variability there is. And this can be seen with the plot here on the left. This first plot right here has 1 degree of freedom, and so the mean here is 1. On average, if we have 1 degree of freedom for our chi-squared distribution, we're going to expect to get a chi-squared statistic of about 1. Now, the standard deviation is the square root of 2, of square root of 2 times 1. And so we can see that it's not very varied. Most of the observations are clustered pretty closely to 1. Now we can still get very large chi-squared values from a chi-squared with 1 degree of freedom distribution, but they're not very likely because there is such a small standard deviation there. The next distribution we're going to look at is the chi-squared with 5 degrees of freedom, and that's this plot here. We can see that the mean now is 5. It has increased. So on average, in the long run, we're going to expect to get a value of around 5 from this distribution. But we can also see that the spread is wider. So there's more uncertainty in this distribution because the degrees of freedom has increased, that has spread out. Excuse me. And we can see that in its relative tail as well. And we can see that as the degrees of freedom goes from 10 to 20, that the mean as well as the mode is shifting farther and farther to the right. So the mean is increasing. So here the mean is 10 and here the mean is 20. But they're also getting wider and wider. So as we increase our degrees of freedom, the standard deviation and the mean both increase. So our distribution has a higher expected value, but there's also a lot more variability or more uncertainty to account for. We can look at this in JUMP as well. So here I have the JUMP distribution calculator. This is the chi-square. We can see that JUMP calls it the chi-square, but we know it's squared distribution. And here it starts off with a default of 4 degrees of freedom. And so that means that the mean is 4. So on average for this distribution, we would expect to get a chi-squared statistic of 4. And that would be this value right here. The standard deviation is the square root of 2 times 4, or the square root of 8, and that's summarizing the approximate spread of this distribution. Let's make this 8. So I'm increasing my mean from 4 to 8. So my degrees of freedom is going from 4 to 8. We can see now that, and I'm actually going to change my scale. So my scale before was from 0 to 18. I'm going to keep my scale from 0 to 18 so that we can get a sense of what is happening. So now we can see that I've got a much bigger spread. Before, everything was much more lumped close around 4, and I had a long tail. Now everything is much more spread out. My variance, because of that increase in my degrees of freedom, my variance has spread things out. So my mean has increased to 8, but my variability around that mean is a lot larger as well. Now let's see what happens if I give myself 100 degrees of freedom. Let's just go crazy. So with 100 degrees of freedom, now we can see that I hardly have anything around 0. So I don't have really, I'm not going to expect or predict a lot of observations very close to 0. And this almost looks like a unimodal and symmetric distribution. I'm going to have a very few observations down here in the left tail, and I'm going to have very few observations up in the right tail either. So as my degrees of freedom increases, this becomes more and more unimodal and symmetric. But don't kid yourself. Remember this first rule. The chi-squared distribution will always have positive values, so it can never be perfectly symmetric. The right tail will always go on to positive infinity, and the left tail always stops at 0. I cannot have anything less than 0. So it might become approximately symmetric, but it will never be perfectly symmetric because I'm never going to go below 0 in the left tail because of that squared property. So as my degrees of freedom increases, especially when I get very large, so that would be like having a lot of rows or a lot of columns in a contingency table, I'm going to get more and more and more symmetric. It's still going to be right skewed, but the skewness is not going to be as apparent. So how do I make these decisions then when I have a chi-squared test? Well, we've just seen that first off, as the degrees of freedom increase, the distribution becomes more bell-shaped, becomes more unimodal and symmetric. But I'm going to say, but it's never perfect because it can't be negative. And so we make our decisions by taking all of these previous things into account. We know that it's always going to be right skewed. It's going to be less obviously right skewed when we have large degrees of freedom, but it is always a right skewed distribution. So we know that larger chi-squared values relative to the degrees of freedom provide stronger evidence against the null hypothesis. But we also have to take into account the fact that as the degrees of freedom increase, the variability or the standard deviation of the chi-squared distribution also increases. So we have to have a much larger chi-squared value relative to the degrees of freedom when we have large degrees of freedom. So for example, if we have, and I'm going to erase some of these arrows here just to clean this up a little bit, if I only have 1 degree of freedom, it's not going to take that much to seem unusual. So a difference of 10 is pretty big. But if I have 20 degrees of freedom and I get a chi-squared statistic of 30, that same absolute difference doesn't seem that unusual because of all that variability with the degrees of freedom. So we have to take into account that extra variability when degrees of freedom increases. So we need to take into account the extra uncertainty, but we're always going to think about the size of the chi-squared value relative to its degrees of freedom, considering the variability based on the degrees of freedom. So we're always going to be looking for large chi-squared values, and we're going to be looking at large relative to the degrees of freedom. A small chi-squared value is not going to be unusual. A small chi-squared value is something that we would expect most of the time. A small chi-squared value means that we have observed something pretty close to what we would expect. Think about this, how we calculated our statistic in the previous video. We're going to pick up in our next video looking at another example doing a chi-squared test for independence.